Today, we are going to journey to the most extreme places in the cosmos, where the very laws of reality seem to get twisted, all to answer one single, really fundamental question.
It kind of sounds like a riddle, doesn't it? But this question pushes physics to its absolute breaking point. You see, to even start to answer it, we have to deal with the biggest disagreement in all of science.
Okay, let's break this down. In physics, we're basically working with two different rulebooks. On one hand, you've got Einstein's general relativity. It's majestic, it's the rulebook for everything big. Planets, stars, you name it. It says space-time is this smooth, continuous fabric. But then you've got quantum mechanics, the wonderfully bizarre rulebook for the very small, for atoms, for particles. And in that world, everything is chunky, it's quantized, it's all about probabilities. Now, these two theories are amazing in their own lanes, but when you try to get them to work together, say when a tiny atom meets the immense gravity of a black hole, yeah, they just don't get along.
To really get a feel for the general relativity side of things, imagine space-time is like a giant, stretched-out rubber sheet. Now, if you put a heavy bowling ball like a star on it, what happens? It creates a dip, a curve. Well, that curvature is what we feel is gravity. It's smooth, it's elegant, and it tells everything else how to move.
Okay, now for the quantum world. Inside an atom, an electron can't just have any old amount of energy it feels like. It's much more like a ladder. The electron can be on the first rung, or the second, or the third. But, and this is key, it can never just hover somewhere in between the rungs. These are what we call discrete, quantized energy levels.
So this brings us right back to our big problem. What happens when you take that quantum ladder, our atom, and you place it deep inside that curve on the space-time sheet, somewhere really extreme, like near a black hole? Do the rungs of the ladder stay the same? Do they get closer together? Do they break? For the longest time, nobody really knew.
And that is where this absolutely brilliant 1980 paper by a physicist named Leonard Parker comes into the picture. He looked at this massive problem and decided to tackle it head-on, performing a calculation that was, well, pretty daring, and for the first time gave us a clear answer.
Parker's setup was, in theory, simple, but the math behind it was incredibly intense. He took the simplest atom possible, just a single hydrogen atom, and he imagined it in free fall, just tumbling through a region of curved spacetime. And then he did something kind of radical for the time. He took the Dirac equation, which is a cornerstone of quantum theory, and he solved it inside the framework of general relativity. His whole goal was to figure out, mathematically, what does gravity's curve actually do to those quantum energy levels?
And what he discovered was, well, it was way more than just a little tweak. The equations revealed something truly profound about the deep relationship between matter and the very fabric of spacetime.
So here's the big takeaway. Extreme gravity doesn't just pull on an atom as a whole object. No, it actually reaches inside the atom and physically changes its fundamental structure. That intense curvature of spacetime literally squeezes and stretches the rungs of that quantum energy ladder we talked about. When you dig into the specifics, it gets even more fascinating. Parker calculated that the energy levels don't all shift by the same amount. The ground state, that's the 1s level, it shifts by one value. But the higher levels, like 2s and 2p, which normally have almost the exact same energy in a hydrogen atom, they get shifted by different amounts. And the result? They actually split apart in a very specific, very predictable way.
And that right there is the key. This is not like a standard redshift, where all the light from something just gets shifted over uniformly. No, this is a differential shift, an internal rearrangement. It's like gravity is leaving a unique, unambiguous fingerprint on the very soul of the atom.
Now, you're not going to feel this effect here on Earth, not even close. Parker calculated that for these gravitational shifts to be big enough to even notice, you'd need a space-time curvature with a radius of just 10 to the minus 3 centimeters. That is an insanely intense environment. We're talking about the kind of gravity you'd only find near a neutron star or right at the event horizon of a black hole.
So this all might seem like a purely theoretical curiosity, right? Just numbers in an equation. But Parker immediately saw an incredible practical implication. This effect could turn a simple atom into an unbelievably powerful tool, a ruler for measuring the universe itself.
So how does that work? Well, every time an electron jumps between those energy rungs in an atom, it either spits out or soaks up light of a very specific color. And this creates a unique spectral barcode for every single element.
It's actually how astronomers can look at a distant star and know exactly what it's made of.
You can probably see where this is going. Imagine you're an astronomer, and you see the light from a cloud of hydrogen gas that's swirling around a black hole. You look at its spectral barcode. If Parker is right, those lines in the barcode won't be where they're supposed to be. They'll be shifted and split in that very unique, predictable way. And by measuring that split, you could calculate the exact curvature of spacetime right at that atom's location. The atom becomes your own remote probe.
As Parker himself put it so perfectly in the paper, atomic spectra carry unambiguous information about the local curvature at the position of the atom. It's like having a direct line of sight into how general relativity works in the most extreme places you can possibly imagine. But the paper leaves us with one last and maybe even deeper idea. It really forces us to ask a tough question about the nature of reality itself and about what we think of as being truly fundamental. Tucked away at the very end of the paper is this absolutely mind-bending statement. He says that the total rest energy of the atom, which, through E equals mc squared we think of as its mass, is itself affected by where it is and how it's moving through curved spacetime. Just think about that for a second. We tend to think of an atom's mass as this fixed, fundamental, constant property. But this calculation shows it isn't. An atom's rest energy, its very being, actually depends on the geometry of the space that it's in. It's not some isolated thing. And that leads us to this final, huge thought. We often think of spacetime as the stage and matter as the actors on it. But what Parker's work shows us is that the stage is actually shaping the actors. The geometry of the entire universe is imprinted on the very properties of the matter inside of it. So, what's really more fundamental, the particle or the space it lives in? It's a question that just shows you how deeply, deeply connected everything truly is.